Imagine somewhere on Earth there is a person who looks exactly like you, with the same voice, the same smile, only different in one thing: their personality is almost completely opposite to yours. In the same way, across the vast space of the universe, there once existed two twin planets, Earth and Venus. Both were born at the same time from the same cloud of cosmic dust, with almost identical size, mass and position. But over time, one world became the cradle of life, while the other turned into an eternal sea of fire. Venus is the mirror reflection of Earth, a planet that might once have been just like us, differing only in the personality that nature and time silently shaped into destiny. Now let us begin the journey to explore Venus to understand why Earth became the home of life, while Venus turned into a burning scar across the sky. In the silence of the early solar system, two planets were born side by side, nearly the same in size, mass and material. They formed from the same dust under the same young sun within the same cosmic nursery. For a time they could have been mirrors of each other, Earth and Venus. Two siblings moulded by gravity and fire. One became a cradle for oceans and breath, the other an inferno. Venus is often called Earth's evil twin, but the word evil belongs to us, not to the cosmos. In truth, it is a reflection, a path that might have been ours. Where Earth cooled, Venus burned. Where we kept oceans, it lost them to vapour and flame. And yet beneath that thick shroud of carbon dioxide and sulphuric clouds, the planet still hides traces of its gentle youth, the echo of rivers that once flowed, the whisper of an atmosphere once kind. Science begins with such echoes. Every signal from Venus is a faint memory wrapped in pressure and heat. The air there presses 90 times harder than Earth's, the temperature high enough to melt lead. The sky glows in tones of amber and blood orange, and lightning dances unseen within the clouds. But in these extremes, something deeper emerges, not just hostility, but the resilience of a world that refuses to vanish. We know that Venus and Earth share almost the same density, the same gravitational pull, even similar day lengths when measured in their slow rotations. Both sit within the delicate line known as the habitable zone, the region where liquid water could once exist. For billions of years they spun together around the same star like two notes resonating in harmony. Then somewhere in that long cosmic song the melody broke. Perhaps the sun brightened just enough to tip the balance. Perhaps a cascade of greenhouse reactions trapped too much heat. Oceans once vast and alive boiled into clouds. Carbon dioxide rose, reflecting heat downward, until the atmosphere became a furnace. The water was lost to space, the surface scorched to stone. We cannot see it directly. The clouds block every wavelength of visible light, turning the planet into a white, featureless sphere from afar. Yet radar and infrared whispers tell another story, a surface surprisingly young, reshaped again and again by forces we barely understand. Some scientists believe that Venus is not dead, merely waiting its crust sealed, but restless, its interior still alive with slow molten tides. And that is the paradox. Two worlds nearly identical at birth diverged into opposite destinies. When you look at Venus tonight, that soft golden spark near the horizon, you're not just seeing another planet, you're looking at a mirror of possibility. A world that might once have been blue, perhaps even filled with seas and storms like ours, now shrouded forever in fire. Maybe in that furnace there is still motion magma pulsing beneath the crust, a quiet heartbeat under miles of crushing air. Maybe the planet that burned itself alive still dreams in silence. We study Venus not only to uncover its past, but to guard our own future. For in its clouds and rocks lies a warning: a world can resemble Earth in every way, and still fall to ruin. Yet the question remains, did it ever truly die? Or is it still breathing, hidden under its sulphur sky, waiting for us to listen closely enough to hear its pulse again? Venus to the human eye is beautiful, a calm pearl glowing softly in the dawn. Yet that glow hides a cruelty beyond imagination. Beneath its bright veil, the air is thick with carbon dioxide and sulphuric acid. The pressure on the surface is 92 times that of Earth, equal to the weight felt 1 kilometre beneath our oceans. The heat is unbearable, more than 460 degrees Celsius, hot enough to melt lead, hot enough to erase history itself. The sky there is not blue. It burns a dim orange, heavy and oppressive. The sunlight that reaches the ground scatters through a haze so dense it looks like dusk at noon. Winds sweep above the clouds at hundreds of kilometers per hour, but down below the air barely stirs. Every breath, if one could breathe, there would be poison. These are not conditions for life as we know it. And yet Venus once might have been gentle. Theories suggest that billions of years ago the planet had ocean-shallow seas that could have lasted for hundreds of millions of years before the runaway greenhouse began. The evidence is locked within its ratio of hydrogen isotopes deuterium to hydrogen far higher than Earth's meaning. Light hydrogen escaped while heavier atoms remained. It is the chemical signature of lost water, a trace of oceans long gone. Imagine a world that once mirrored our own clouds of water, perhaps rainfall, maybe even a coastline. Then, as the sun brightened, evaporation rose faster than the atmosphere could handle. Water vapor, a powerful greenhouse gas, trapped more heat. The oceans fed the fire and the feedback loop began. Within a geological blink, Venus transformed from a temperate twin into a global furnace. Science calls this the runaway greenhouse effect, a chain reaction, where rising temperatures cause even more heat to be trapped, until equilibrium becomes impossible. The carbon dioxide once dissolved in oceans or locked in rock was released into the air. The surface melted, then hardened into basaltic plains, vast frozen waves of lava. The question that still lingers is not why it happened, but whether it ever truly stopped. If Venus burned once, could it burn again from within? To understand, scientists look for clues, not only in the atmosphere but beneath it, through radar, through infrared, through the faint shifts in heat that betray motion. Each observation hints at something contradictory, a surface too young, a crust too smooth. If the world were truly dead, its scars should be countless. Instead, it appears renewed. How does renewal exist in a place where nothing survives? Perhaps that is the paradox of Venus' destruction and rebirth woven together. The very forces that destroyed its oceans may still sculpt its surface. Magma may rise and cool beneath pressure so immense that no mountain can crumble. Volcanic plains stretch for thousands of kilometers, suggesting that the planet's heart remains molten, restless, alive. In this inferno, chemistry itself becomes strange. The clouds above are filled with acid droplets swirling in endless circulation. Lightning flashes in bursts, charging the upper atmosphere with static. Carbon dioxide crushes everything below, but in those chaotic reactions, sulfur and carbon still dance a violent continuous alchemy. Venus is not simply a planet of death. It is a living laboratory, a glimpse into what happens when the balance of climate is lost, when energy overwhelms stability. Studying it means studying the edge of habitability itself. It forces us to ask what truly defines a living world. Breath ocean's motion beneath the crust, or simply change the capacity to evolve even through fire. Perhaps Venus never died at all. Perhaps it was reborn in a form we can no longer recognize, a mirror of endurance, not failure. When we stare through telescopes and see its pale glow, we are not witnessing a corpse drifting through space. We are seeing a survivor, still burning, still transforming a planet that reminds us that life and death in the scale of the cosmos are only phases of the same eternal experiment. If Venus is a world of fire, why do we keep listening? What could humanity possibly learn from a planet that crushed every probe we sent, that turned oceans into vapor and rock into rivers of molten glass? The answer begins with curiosity but ends with survival. Venus is the closest planet to Earth in both distance and essence. Its gravity size and composition mirror ours so precisely that scientists often call it our control experiment in planetary evolution. If two worlds start the same, then their differences reveal the fragile conditions that keep one alive. Studying Venus is like reading an alternate version of our own story, one written in ash. Every planetary mission that seeks new life, every telescope that peers into the darkness of exoplanet systems, carries with it a question whispered by Venus. What went wrong? When astronomers look beyond our solar system, they find hundreds of planets similar in size and orbit to our own. Many orbit their stars within what we call the habitable zone, the narrow region where liquid water could exist. But numbers deceive. Some of those worlds may be more like Venus than Earth, warm-clouded, heavy with carbon dioxide. That is why scientists now speak not only of habitable zones, but of Venus zones, orbital distances where a planet could once have been Earth-like before tipping into catastrophe. To identify these worlds, we must understand the process of transformation itself, the delicate threshold where climate shifts from balance to runaway collapse. Venus is that threshold made visible. The lesson it offers is not about despair but perspective. Our atmosphere on Earth holds traces of the same gases, the same mechanisms, the same possibilities. Venus is not a warning carved in myth. It is physics, chemistry, inevitability. It shows us that climate and geology are not passive. They are living systems, responsive and unstable. Given enough energy, any world can rewrite its own fate. Yet Venus also hides the blueprint of resilience. The planet has persisted for billions of years under forces that should have torn it apart. Its thick atmosphere shields it from meteoroid impacts. Its rotation, slow and strange, may help redistribute heat. Beneath that pressure, minerals form structures unknown on Earth. Even in the upper atmosphere, 50 kilometers above the surface, temperatures drop to near-Earth conditions and their strange chemistry unfolds. Phosphine, a molecule difficult to explain through inorganic means, was once detected a fleeting hint that complexity might still flicker within the acid clouds. Whether that detection was true or false matters less than what it reveals about our hunger to know. Venus challenges us to keep questioning, to refine our instruments, to listen more carefully. It pushes science to its edge where certainty dissolves and imagination takes over. Somewhere in that tension between data and dream, the planet becomes more than a subject. It becomes a mirror of humanity itself, stubborn, destructive, still reaching for understanding even in ruin. We listen to Venus not because it comforts us, but because it unsettles us. It shows how thin the line is between paradise and inferno, between balance and collapse. It reminds us that habitability is not guaranteed, that every breath of air and drop of water on Earth exists by the narrowest margin. And perhaps in that recognition we find humility, the kind that comes from knowing how easily beauty can turn to silence. Venus speaks through heat, through pressure, through the quiet hum of radar echoes. Its voice reaches us across space, distorted, muffled, but unmistakably alive. We may never walk its surface for more than a few trembling minutes, but through every signal we touch its memory. The planet once shared our beginning. Maybe through listening it will help us understand our ending or how to prevent it. For centuries, Venus was a mystery sealed in light. To every telescope on Earth it appeared smooth, flawless, a perfect white sphere that never revealed a single scar. Its brilliance made it the brightest object in our night sky after the moon, yet also the most secretive. No mountain range, no crater, no ocean shimmer ever showed through the haze. The reason was simple and absolute: clouds. A planet wrapped in an unbroken layer of acid and carbon dioxide, stretching more than 20 kilometers thick, reflecting nearly all sunlight back into space. To the human eye, Venus is pure brightness, not because it glows, but because it hides. If you could descend through that veil, the illusion would end. At first, you would see soft, milky light scattering around you like being inside a sunlit fog. Then the glow would deepen into orange and the air would grow heavy, hotter, thicker with every kilometre. The clouds would change from droplets to smoke, the brightness dimming into the copper twilight of a perpetual dusk. By the time you reached the surface, the world above would vanish. The horizon would melt into haze, the sky no longer a window but a weight. That is why observation from afar is so difficult, light cannot escape. What we know of Venus was not seen by eyes but by echoes. Scientists had to learn to hear the planet instead of seeing it. Radar became their language. It began with Pioneer Venus 1 in 1978, which sent pulses of radio waves toward the surface and listened for their return. Each signal bouncing back with a subtle delay revealed contours, ridges, plains, craters invisible to optical telescopes. Later, the Magellan spacecraft transformed this method into art. Between 1990 and 1994, it mapped nearly the entire planet with radar vision, its microwaves cutting through the sulfuric clouds like invisible light. The images that emerged were both stunning and alien. Instead of seas or continents, Magellan saw endless plains of solidified lava mountains taller than Everest, and circular scars hundreds of kilometers wide. The surface was smoother than Earth's, but strangely uniform, as if some immense event had melted and reset everything. The radar beams revealed brightness where the terrain was rough, darkness where it was smooth. Scientists compared those patterns, stitched them into maps, and realized that nearly 75% of the planet was volcanic plain. What the eyes could never see, the radio waves had uncovered the fingerprints of a restless world beneath the clouds. Still, each measurement carried uncertainty. The thick atmosphere distorts echoes, temperature gradients bend waves, surface minerals scatter signals in unpredictable ways. It's like trying to reconstruct a landscape by shouting into a cave and measuring the echoes that return. Yet even those imperfect signals built the foundation of modern Venus science. Every contour, every elevation reading every crater now catalogued came from sound, not sight. And what they suggested was unsettling. The surface appeared far younger than expected. Few impact craters, vast volcanic regions, and a strangely uniform texture pointed to a mystery the planet had erased much of its history. To study Venus is to accept that knowledge will always be partial. The planet teases us with fragments, hints that flicker between data and noise. But even these fragments have reshaped how we view other worlds. If we can learn to see through Venus's clouds, if we can translate the echoes of a furnace into knowledge, then perhaps we can see through the veils of countless exoplanets, too hidden under their own storms. In that sense, Venus is not only a planet, it is a method, a way of learning to look into darkness and find patterns where no light exists. And behind those patterns lies the next step in the search, how to read the faint warmth of a world we cannot touch and discover whether its heart still beats. If light cannot reach Venus's surface, then we must listen to it instead. Radar became our voice in the dark, a scientific form of echolocation, a language built on reflection and delay. Where the eye fails, sound in the form of radio waves reveals what lies hidden. When Pioneer Venus 1 first aimed its antenna toward the planet in 1978, it was as though humanity whispered into a storm. Radio pulses struck the thick atmosphere, vanished, and then returned faint, distorted, but filled with information. From those echoes came the first outlines of a world no one had ever seen. Then came Magellan. In 1989, NASA launched the spacecraft that would for the first time see through the planet's veil. Magellan orbited Venus for 4 years, bouncing radar waves toward the surface and recording how they scattered. Each signal told a story about texture, slope, and composition. Bright reflections meant rough terrain cliffs, lava flows, or fractured plateaus. Dark regions suggested smoother plains, perhaps ancient seas of cooled basalt. Over time, those millions of radar echoes became a map, not a photograph, but something more like a pulse record, a seismic heartbeat turned visual. The entire surface was charted with resolutions fine enough to identify structures only a few hundred meters across. Mountains, ridges, coronae, vast circular features that no one could explain all emerged from data alone. It was through Magellan that scientists discovered just how volcanic the planet truly was. 3/4 of Venus is covered in hardened lava plains, more than 1/700 volcanoes large enough to see from orbit, and countless smaller vents scattered like freckles across its face. Some stand alone, others cluster in regions of chaos, networks of fractures, domes and valleys suggesting immense ancient flows. And yet among these findings came a paradox. If Venus were dead, geologically silent for billions of years, then these volcanoes should be relics. But radar measurements revealed surfaces that looked fresh, their reflectivity suggesting relative youth. No erosion, no dust from eons of impacts. Something had erased the old scars. Radar alone cannot confirm activity, but it gives hints, subtle variations in brightness, shifts in reflectivity that might mark cooling lava. Each of those variations became a whisper of possibility. Maybe Venus is not frozen in its past. Maybe somewhere beneath those crushing clouds, new land is still being born. But radar does more than detect shape. It measures movement. By firing signals at the same locations over time, scientists can detect minute changes, a slope that bulges a crater, that darkens a region, that reflects light differently than before. These changes may point to flows of magma, collapses of crust, or gases vented from below. Such comparisons take patience. Magellan's data from the early 1990s is still being re-examined with modern algorithms, each update sharpening the picture. New techniques reveal hints that some volcanic vents have indeed changed shape or brightened as if lava cooled there only decades ago. To imagine radar as vision is misleading. It's closer to touch. It feels the contours through waves, sensing pressure and return like fingertips brushing over unseen stone. Through it, Venus becomes not an image but a sensation, dense, textured, alive. These instruments transform the planet from myth into measurement, from a symbol of beauty into a laboratory of extremes, and through them we learned that knowledge is not always bright. Sometimes it must echo back from the dark. When the last signal from Magellan faded in 1994, the spacecraft plunged into the atmosphere it had spent years studying vaporized in the same inferno it had revealed. but its legacy endures. Every map, every elevation model, every hint of motion beneath the clouds traces back to its echoes. Through radar, we learn to listen to a world that cannot speak in light, and what we heard was not silence, but a pulse steady distant, still beating beneath a veil of fire. Even through radar's precision, Venus remained incomplete, a world drawn in sound but still mute in warmth. To understand whether it was truly dead or merely sleeping, scientists turned to another messenger heat. Infrared light, the faint glow of warmth radiating from a surface, became our next sense. Unlike visible light, certain wavelengths of infrared can slip through the densest parts of the Venusian clouds, revealing temperature and energy, the slow exhalation of stone. The Venera Express mission, launched by the European Space Agency in 2005, carried instruments tuned to this glow. For almost 8 years, it orbited Venus and listened for heat mapping the brightness of the planet's surface through its dense atmosphere. What it found startled scientists. Across the volcanic plains, the planet's thermal signature was uneven. Some regions, especially those surrounding large volcanoes like Matterhorns and Ozomons, shone slightly warmer than expected. The differences were small, just a few degrees, yet meaningful. In a world where convection and pressure should erase temperature contrast, these hotspots hinted that the surface itself might still be cooling from recent activity, or heating again from below. Infrared data doesn't capture images as our eyes do. It captures stories of energy. Each wavelength corresponds to the vibration of molecules, the slow trembling of matter giving off its final light. Through these vibrations, scientists could estimate the age of rocks. Younger flows radiate differently than ancient ones. The results suggested that some lava deposits might be astonishingly recent, not hundreds of millions of years old, but perhaps less than 2 million. In geological time, that is yesterday. Imagine standing above a plain of cooled basalt beneath a sky of burning amber. You place your hand upon the stone and feel warmth that should have long since faded, warmth that should not exist. That is the feeling. The data evoke the suspicion that Venus is not an extinct world, but one still alive in secret. The Venera Express also watched the night side of the planet, where thermal radiation escaped most freely. Patterns appeared and shifted, subtle but real, like embers breathing beneath ash. These variations suggested dynamic processes, either volcanic outgassing or convection in the crust. The observations were indirect, uncertain, but persistent. Every orbit added another whisper to the same refrain: the planet may not be silent. Infrared mapping revealed another truth as well: how energy circulates between the surface and atmosphere. On Venus, this relationship is brutal and intimate. The air is so dense that it smothers the land. Each layer presses downward, trapping heat that the rocks try to release. The result is a world that glows from within its entire surface, radiating the same deep orange heat, like an ember wrapped in glass. Infrared light, invisible to our eyes, carries both the evidence of motion and the poetry of decay. It shows where the planet breathes, where it holds its fever. Scientists sometimes call it the language of the surface, for it translates temperature into meaning, the only language Venus still speaks. Together, radar and infrared form a duet. One measures shape, the other energy. One maps the solid, the other the restless. And between them lies the truth we seek, whether the planet's stillness is final or merely an illusion. Every mission to Venus since then, every proposed orbiter and lander owes its strategy to that insight. To read the planet, we must combine sound and warmth, geometry and glow. And yet, for all the precision of our instruments, what they reveal is not an end but a threshold. Each discovery, the fresh flows, the faint warmth, the uneven glow, leads to the same question: how can a world so hostile still move beneath its scars? The data cannot yet answer. But in the soft infrared shimmer that escapes from beneath the clouds, scientists hear a promise. Something within that inferno still turns, still changes, still burns. And through the darkness, the planet keeps whispering its oldest secret, that even in silence heat remembers. If Venus were an ancient lifeless world, its face should be pocked with scars. Every solid body in the solar system, Mercury, Mars, even our moon, bears the marks of its long history. Craters upon craters, evidence of eons of cosmic bombardment. The older a surface, the more scars it carries. Time in the language of planets is measured in impacts. But when the radar maps from Magellan were first stitched together, scientists were stunned. Venus was nearly smooth. The number of impact craters was astonishingly small, barely 1,000 across the entire planet. For comparison, the Moon hosts hundreds of thousands. Even Mars, smaller and less geologically active, carries more than 30 times that number. Something was wrong. Either Venus had somehow avoided billions of years of collisions, or something had wiped its history clean. At first, the dense atmosphere seemed an obvious explanation. The planet's thick blanket of carbon dioxide laced with clouds of sulfuric acid could burn and crush small meteoroids before they reached the ground. And indeed, many small impacts never make it through. The friction of entry vaporizes them in bursts of plasma long before they touch the surface. But the atmosphere cannot stop everything. Large asteroids several kilometers wide should still strike with devastating force, and yet even those are missing. There are too few craters of any size. The data forced a different conclusion. Venus's surface is young, geologically young, no more than a few 100 million years old. To scientists, that number is shocking. If Earth's crust records 4.5 billion years of tectonic shifts and volcanic cycles, Venus seems to have pressed reset on its geological history sometime in the recent past. What could cause an entire planet to start over? Some call this the Great Resurfacing, a period when most of the crust was destroyed, melted, or buried beneath oceans of lava. But the evidence is indirect, inferred from the distribution of those rare craters that remain. They are scattered randomly, not clustered as they should be if the planet had slowly renewed itself. Random distribution means a single global event, one that erased almost everything at once. Imagine the violence the crust fractures, magma surges upward, the atmosphere fills with volcanic ash and molten droplets. Entire continents, if such things ever existed, would vanish under flood basalts kilometers deep. Within a few millennia, the world would cool again, smooth, unblemished, as if reborn. It is difficult to picture such an event on Earth. Even our greatest volcanic epochs like the Deccan Traps or Siberian Traps reshaped only parts of the globe. But Venus shows signs of a catastrophe on a planetary scale, a reset so complete that even the memory of older mountains is gone. This resurfacing leaves behind paradoxes. The surface looks young, but the planet itself is ancient. The crust appears stable now, but it must once have been fluid and alive. And under that stable skin, heat still lingers, the same heat that might once have forced the world to erupt in a single convulsion. The few craters that do exist tell their own story. Some are pristine with sharp rims and ejecta patterns stretching for hundreds of kilometers. Others appear distorted, their edges softened by flows of lava that came later. A few craters even seem half buried, as if the surface continued to move after impact. These are not relics of a dead planet. They are clues in a mystery still unfolding. Every crater on Venus is in a sense a clock. By counting them and comparing their densities to other worlds, scientists estimate the planet's surface age somewhere between 150 million and 1 billion years. That wide range reveals both our ignorance and the planet's secrecy. Venus does not offer clear answers. It gives us contradictions wrapped in heat and pressure. And so, the paradox remains: a world old enough to remember the birth of the solar system, yet wearing the face of a planet reborn. If that resurfacing truly happened, then somewhere within Venus lies the reason, a mechanism powerful enough to melt continents, yet silent enough now to leave the planet still. It is the greatest riddle of Venusian geology. What force can destroy the surface of a world and then let it sleep again? Every world renews itself in some way. On Earth, the crust moves, breaks, and sinks. Oceans open and close. Continents drift. Volcanoes rise and die. Time erases the scars of impact because our planet is alive, its skin constantly reshaped by plate tectonics and erosion. But on Venus, neither of those forces seems to work. The radar maps show no continents drifting, no trenches pulling old crust downward, no fractures dividing the planet into shifting plates. The surface is one immense slab, fused and rigid, locked beneath a pressure so great that no ocean, no mountain range, no wind could carve it. At first glance, it feels static, a frozen world beneath its raging sky. Yet that stillness only deepens the mystery. If there are no tectonic plates, no erosion, no weather strong enough to sweep away the craters, then what erased them? The search for answers began with elimination. The first suspect was erosion. Could wind, even under such crushing atmosphere, have worn away the old surface features over hundreds of millions of years? But Venus's winds are deceptive. High above the clouds, they race around the planet at hurricane speed, 300 kilometers per hour. But near the ground, the air is so dense that it hardly moves at all. Even a gentle breeze carries the force of a hurricane, yet the flow is slow, laminar, more like syrup than air. It shapes dunes and smooths small ridges, but it cannot erase an impact crater tens of kilometers wide. Next came chemical weathering, the slow corrosion of rock by the acidic atmosphere. Sulfuric acid and carbon dioxide react with minerals, altering them into new forms. But again, the pace is glacial, far too slow to account for the wholesale absence of ancient terrain. If wind and chemistry fail, perhaps subduction, the sinking of crust into the mantle, could do the job. But every line of evidence says otherwise. The surface shows no deep oceanic trenches, no chains of subduction volcanoes like those on Earth. The planet's crust appears continuous, a single unbroken shell. Beneath that shell, convection in the mantle may still churn, but with no way to vent or recycle, the heat simply builds. It is a geological paradox, a planet that traps its own energy. Without moving plates to release it, gradually Venus becomes a pressure cooker. The heat from radioactive decay accumulates, the mantle grows restless, and eventually something must give. That stored energy may explain the great resurfacing. When the internal pressure exceeds the strength of the crust, the entire shell could fracture at once, letting magma surge upward globally. For a brief geological moment, the planet might convulse, lava flooding across plains, burying old craters, smoothing everything into a near-featureless expanse. Afterward, the crust solidifies again, sealing the planet once more in stillness. The cycle resets. On Earth, this heat escapes gently through thousands of volcanoes and the slow drift of continents. Venus, without those valves, waits in silence until it bursts. Some researchers describe this process as episodic, resurfacing long eras of quiet, interrupted by catastrophic renewal. Others imagine a more gradual pattern, with isolated volcanic provinces erupting over time, each one reshaping a region before going dormant again. But none of these models fit perfectly. The surface features we see, coronae lava plains, shield volcanoes, tell fragments of the story, but not the ending. Each theory tries to reconcile the same facts. The lack of craters means renewal. The lack of tectonics means confinement. The result must be an extraordinary release of heat, one powerful enough to melt continents. Yet even that explanation carries doubt. If the resurfacing was catastrophic, why don't we see the chaos left behind? The surface today looks stable, calm even. Its smooth plains suggest that the eruption ended long ago, perhaps hundreds of millions of years. But is it truly over? Or are we living in the pause between breaths? Venus defies our models because it follows none of them completely. It behaves like a planet still alive, yet looks like one that has died. It shows signs of fire, but wrapped in stillness. It preserves the marks of motion, but no motion itself. And so, science circles back to its paradox. If every known mechanism of planetary renewal fails, perhaps Venus created its own. A system that holds its fury until the world itself can no longer bear it, and then in one cataclysmic instant remakes itself anew. The next step is to ask whether that fury has truly ended. For if it has not, then somewhere beneath the smooth plains and dense air, magma may still move slow, patient, unseen. And if it moves, then Venus is not finished with its story. It is only waiting for its next chapter to begin. When every other explanation fails, one remains fire. If wind erosion and shifting plates cannot account for Venus's youthful face, then the planet must have rewritten itself from within. It must have melted and cooled again, erasing its own past with lava. Radar images from Magellan showed what no human eye could see, an entire world sculpted by volcanoes. 75% of Venus's surface is paved in basaltic plains, the frozen remains of ancient flows. Thousands of volcanoes, some as wide as countries, some delicate as domes, scatter across this landscape. More than 1,700 large volcanic structures have been catalogued, and many more lie beneath the haze, their outlines blurred but unmistakable. Here lies the heart of the volcanic hypothesis, the idea that Venus's smooth, crater-sparse surface is not the result of slow erosion but of global fire. At some point in its history, the planet's crust may have ruptured, releasing enough magma to bury its entire exterior under fresh rock. The evidence is everywhere. In the radar maps, bright streaks reveal channels that stretch for hundreds, even thousands of kilometers, rivers of lava longer than the Nile. Circular mountains rise with gentle slopes, shield volcanoes built by eruptions that lasted for centuries. Others take strange shapes, steep-sided domes called pancake domes, formed from thick, viscous magma that oozed upward and solidified in place. These structures suggest a variety of volcanic processes, some similar to Earth's, others utterly alien. The absence of tectonic boundaries means Venusian volcanoes don't form in chains like those of the Pacific Ring of Fire. Instead, they appear scattered evenly across the planet as though magma seeps upward wherever it can through cracks in the stagnant crust, through weaknesses that shift as internal heat builds. If this model is correct, then Venus has no geological rhythm. It doesn't breathe in cycles like Earth. Instead, it holds its breath for eons until the pressure becomes unbearable. Then, in one catastrophic exhale, it covers itself in fire. The thermal inertia of such a planet is immense. Once a global eruption begins, it could last for tens of thousands of years, fed by mantle plumes rising from deep within. The entire surface may have been resurfaced in an event geologically brief, perhaps less than 1% of the planet's age. Afterward, as the crust thickened and cooled, the lava plain solidified into a world of stillness. The atmosphere, already thick, grew heavier, with gases released during the eruption. Carbon dioxide, sulfur dioxide, water vapour, all trapped under a lid of heat. The runaway greenhouse intensified. The oceans, if they still existed, boiled away for the last time. Venus had not been destroyed by an external impact. It had consumed itself. The remnants of that cataclysm are visible in features scientists call coronae, immense circular patterns, sometimes hundreds of kilometres wide, that mark where magma pushed upward, but failed to break through. Seen in radar images, they resemble crowns or halos fitting, since the word corona means crown in Latin. Around them, cracks radiate outward like sunbursts, frozen moments of strain in the planet's crust. These coronae may be the fossilized breath of Venus's inner life, the places where it once tried to rise, to vent, to relieve the pressure locked beneath. If so, they are not signs of death but scars of struggle. Other strange forms accompany them, arachnoids, intricate networks of fractures that look eerily like spiderwebs. They may represent partial eruptions, places where magma pooled just below the surface, warping the crust but never escaping. Together, these features tell a consistent story. Venus's surface was not merely melted once. It is patterned by repeated uneven attempts of the mantle to break free. Each eruption changed the landscape. Each release reshaped the atmosphere. Volcanoes became the architects of both surface and sky, and perhaps in some places they still are. Recent analyses of Magellan's radar data show slight changes in reflectivity around certain volcanic vents, as if the terrain there has darkened or brightened over time, the possible fingerprint of cooling lava. Later missions observing in infrared found heat anomalies near the same regions. The hints align with one another, pointing to a quiet but persistent truth: the fire has not gone out. If this is so, then Venus may still be active, not in explosive eruptions, but in slow, silent flows beneath the surface. The planet's heat, trapped for ages, finds tiny fractures through which to breathe. Each exhalation releases gas into the dense atmosphere, feeding its chemistry, maintaining the balance of hell. We call it the volcanic hypothesis, but it is more than a theory. It is a portrait of a world that never stopped remaking itself, a planet that lives through destruction, that survives by burning. Venus, Earth's twin, did not die young. It transformed from a world of oceans into a furnace of stone, from a place of light to a monument of heat. And within that transformation lies the truth of all planets: to endure, sometimes you must begin again in fire. There are shapes on Venus that exist nowhere else in the solar system. They're vast, circular and intricate, not the clean rings of impact craters, but complex mosaics of fractures, ridges and plateaus that ripple across the planet's surface like frozen waves. Scientists call them coronae, from the Latin word for crown. The name fits. Each one looks like a halo pressed into stone. Some stretch for hundreds of kilometers, bordered by concentric cracks that curve outward like petals. Others overlap, weaving patterns so chaotic they resemble fingerprints burned into the crust. To the radar eyes of the Magellan spacecraft, they appeared bright and sharp, luminous, against the darker plains of solidified lava. No one had ever seen such formations before. On Earth, no mountain, no volcano, no tectonic fracture behaves this way. And yet across Venus, these crowns are everywhere. They defy simple explanation. At first, scientists thought they were collapsed volcanoes, the remnants of ancient calderas that had sunken inward after eruption. But the structures were too broad, too shallow, too layered to fit that model. Others suggested they might be the result of gigantic impacts, but their symmetry was wrong. No central peaks, no ejecta blankets. Eventually a new theory emerged, one that linked them to the restless interior of the planet. Each corona it proposed is the footprint of a mantle plume, a rising column of molten rock that pushes against the crust from below. As the hot material swells upward, it bulges the surface, fracturing it in concentric rings. Then, as the plume cools or retreats, the raised terrain collapses inward, leaving a circular pattern of ridges and fractures behind the fossil of an ancient breath. If that is true, then every corona marks a place where Venus once tried to breathe. A pulse, a heartbeat. A moment when the planet's inner heat met the unyielding crust and left its signature before sinking back into silence. The variety of these forms is astonishing. Some coronae are immense, like Artemis, stretching nearly 600 kilometers wider than the continental United States. Others are small and clustered, forming chains across the volcanic plains. Some are bright with radar reflection, their edges crisp and young. Others are blurred and faint, softened by later lava flows. Together they record a story of motion and resistance of a planet struggling to express its heat through a solid shell that refuses to open. But the deeper mystery lies in their arrangement. Unlike Earth's volcanoes, which cluster along tectonic boundaries, Venus's coronae are scattered almost evenly across the globe. They do not align with continents or rifts because such divisions do not exist here. Instead, they form a planetary mosaic, each a vent that opened and closed independently, guided only by the slow currents of the mantle below. To study them is to glimpse a world ruled by internal chaos rather than external order. Every pattern hints at a different stage in the life cycle of a plume. Some coronae are surrounded by vast plains of lava, suggesting they once erupted violently. Others sit in isolation, mere depressions encircled by cracks, failed eruptions perhaps where magma rose but never broke through. The arachnoid's smaller web-like structures often found near coronae deepen this strangeness. Their fine radial lines resemble the threads of a spider's web stretched across stone. Scientists believe they too form from magma that pushes upward but fails to reach the surface, warping the crust in delicate fractal patterns. These formations are not random art. They are the language of stress and release. Each curve and fracture encodes how the planet's interior once moved. Each circle is an echo of motion we can no longer see. And through them, a picture emerges of Venus not as a dead world, but as one frozen mid-motion caught between eruption and stillness. Imagine standing upon one of these crowns of fire. The ground would be endless rock fractured in every direction. The air would crush your body within seconds. The light would be dim amber, as though the planet itself glowed. And under your feet, somewhere deep below, the memory of molten motion would wait heat trapped beneath a crust that has forgotten how to yield. That is the paradox of the coronae. They are monuments to motion, yet they exist in a place where nothing moves. To some scientists they are fossils, to others they are warnings. For if mantle plumes still rise beneath Venus today, then these patterns are not just remnants. They are living scars shifting ever so slightly beneath the surface, invisible but alive. The crowns of Venus remind us that fire, even when buried, does not forget how to burn. It simply waits. Beneath the silent surface of Venus, something stirs. The radar maps, for all their clarity, cannot pierce the depths, but the patterns above hint at a restless interior. Every corona, every vast plateau and circular fracture seems to whisper the same truth. There are forces rising from below, pushing against a crust that refuses to break. These forces are known as mantle plumes, immense columns of molten rock that rise slowly from the planet's interior like candle flames that never extinguish. On Earth, such plumes form the volcanic islands of Hawaii or Iceland, places where magma wells up independently of tectonic plates. But on Venus, where no plate boundaries exist, these plumes have no guided path. They move freely, driven only by the heat trapped in the planet's heart. Scientists suspect that beneath the thick, motionless crust of Venus, dozens, perhaps hundreds of such plumes might exist, slowly swelling, deforming the surface above. They do not always erupt. Most of the time they remain ghosts, unseen, unfelt, but powerful. Their energy builds pressure beneath the crust, creating bulges, ridges, and circular fractures, the very geometry of the coronae that scatter across the planet. To imagine this process is to picture a world breathing in stone. Each plume rises for millions of years, pushing against the crust like a tide. If the crust is weak, magma breaks through, flooding the plains in sheets of lava. If the crust is strong, the magma stalls trapped just below the surface, leaving behind the circular deformations we now see from orbit. The distribution of these plumes poses another puzzle. Unlike Earth, where volcanic activity follows predictable lines, Venus's volcanoes are evenly spread across the globe. It is as though the entire planet is heated uniformly from within, like an ember glowing through a thick shell. The pattern suggests not localized activity but global convection, a mantle that churns as one immense sluggish ocean of molten rock. This model changes how we understand Venus. Instead of a planet covered by individual volcanic provinces, it becomes a single interconnected system, a sphere of slow, suffocating motion. Each plume influences the next, their rising and sinking flows locked in a rhythm that lasts millions of years. When one region cools, another heats. When one plume fades, another swells in its place. To test these ideas, researchers analyze the subtle variations in topography, gravity, and radar reflectivity across the surface. The brightest regions like Beta Regio, Atla Regio, and Western Isla Regio stand higher than the surrounding plains. They coincide with concentrations of coronae domes and volcanic vents, the fingerprints of active mantle upwellings. Beta Regio, for instance, is crowned by Ria Mons, a massive volcano surrounded by fractured terrain. Atla Regio, home to Matmons and Ozermons, appears even more dynamic. Its radar brightness changes slightly between observations, and infrared studies show it radiates more heat than nearby regions. If any place on Venus is still active, this may be at a province where plumes rise close enough to the surface that the crust begins to breathe again. But these are hints, not proof. To confirm a living plume, one would need to detect motion, the slow uplift of the surface or the release of gases that betray magma below. So far, no spacecraft has stayed long enough or seen clearly enough to measure such changes. Still, the evidence accumulates. The symmetry of the coronae, the distribution of volcanic plains, the faint thermal anomalies all converge toward the same possibility: Venus's interior remains alive. Not in the violent plate-driven way of Earth, but in a deep constrained rhythm, heat building, crust-bending pressure rising. If this interpretation is correct, then the planet we once thought of as static is in fact dynamic beneath its stillness. Every fracture and ridge becomes a sign of suppressed motion, every circular depression a sigh in the planet's long exhale. The plumes of Venus are not just geological curiosities, they are the engines of its fate. They decide when the surface renews, when gases escape, when the balance between crust and mantle shifts again. And one day, perhaps millions of years from now, or perhaps far sooner, one of these plumes may find a weakness. It will rise a little higher, push a little harder, and the cycle will begin anew. The crowns of fire will open again. Lava will flow and the planet will breathe once more. Venus teaches us that silence is not the same as death. Beneath even the stillest crust, motion waits slow, patient, inevitable. And when that motion finally breaks through, the world will remember how to burn. Across the face of Venus, volcanoes and coronae are scattered in a pattern that defies order. There are no chains, no arcs, no lines marking where continents collide or oceans open. Instead, the planet's volcanoes seem to float evenly distributed, spread like freckles across a single seamless skin. This uniformity is more than aesthetic. It is a revelation. It tells us that Venus, unlike Earth, has no tectonic boundaries, no deep scars dividing crust from crust, no drifting continents to guide the motion of magma. The entire surface is one unbroken plate, a continuous shell of rock that locks the planet's energy inside. It is this continuity that makes Venus both beautiful and dangerous. On Earth, plate tectonics acts as a safety valve. The crust fractures, heat escapes, and the planet exhales. Mountains rise, oceans form, and carbon is recycled from rock to air and back again. But Venus has no such relief. It holds its breath. And when a world holds its breath too long, pressure becomes destiny. Scientists have studied the global maps from Magellan and Venera missions, plotting every volcano, every rift, every corona. The result is startling. These features appear almost evenly spaced, like the pattern of bubbles beneath a cooling surface. This suggests that the planet's internal heat doesn't escape locally, it pushes outward everywhere with equal force. Imagine the entire mantle of Venus as a single convecting sea of magma. Wherever a plume of heat rises, it presses on the crust. The crust bends, fractures, then slowly heals. Because there are no plates to separate or collide, the planet's interior heat distributes itself evenly, a global network of invisible breathing points. That is why on Venus volcanic activity seems random and universal. It is not guided by geography, but by physics. Every region has the potential to awaken. This even distribution explains the haunting sameness of the surface. From pole to pole, the radar images show the same patterns of smooth plains and broad ridges, as if one geologic hand had reshaped everything at once. The absence of continental contrasts, no granite highlands, no oceanic basins gives the planet its eerie uniformity. It is a world without borders, a canvas of pure basalt painted entirely in fire. Yet within that apparent simplicity lies complexity beyond measure. The coronae themselves cluster into provinces of activity, vast highlands like Beta Regio, Themis Regio, and Atla Regio, where plumes rise closer to the surface. Each region may represent a breathing zone, a place where the crust flexes in response to rising magma below. Between these zones stretch the smooth lava plains, cooled and ancient like the calm surface of an ocean after a storm. The balance between these regions may define the planet's rhythm. When one area releases heat, another grows still. When the plumes beneath Atla Regio weaken, perhaps those under Beta Regio swell. The system compensates, seeking equilibrium in the absence of tectonic motion. It is not chaos, but a slow distributed order, a planetary heartbeat spread across the entire sphere. This uniform volcanism also explains why Venus's atmosphere remains thick and oppressive. Everywhere the crust opens, gases escape: carbon dioxide, sulfur, dioxide, traces of water vapor. Without oceans or weather systems to trap them, these gases build over time, feeding the greenhouse effect that defines the planet. Each volcanic breath thickens the air, turning the surface into an even deeper furnace. In this way, the geological and atmospheric systems of Venus are inseparable. The volcanoes feed the sky traps the heat feeds the volcanoes again. It is a perfect, terrible feedback loop, one that might once have been stable, but now sustains itself endlessly. This planetary design, smooth-sealed, self-contained, is both genius and curse. Without tectonic fragmentation, Venus avoids earthquakes and drifting continents, but it loses renewal. Its crust does not recycle, it suffocates. Its mantle does not rest, it seethes. And every few 100 million years, the balance tips, the shell fractures, the plumes erupt and the planet resets. A world without boundaries becomes a world without mercy. Still, there is a strange serenity in this vision. From orbit, Venus looks tranquil, a glowing cloud-wrapped sphere, motionless and perfect. The chaos below cannot be seen, only inferred. It is a beauty built on pressure, an equilibrium maintained through fire. Perhaps that is the essence of Venus unity at the cost of freedom. A planet that remains whole because it cannot change until the moment it must. Somewhere beneath that continuous crust, the next eruption is already beginning, slowly and invisibly. And when it comes, the entire planet will move all at once, a single plate exhaling in unison, rewriting itself again in the language of lava. Venus is a planet that cannot cool. Its surface glows faintly with stored energy, its atmosphere presses like a weight of stone, and beneath that unbroken crust heat accumulates, trapped, unable to escape. On Earth, the flow of heat from the interior is gentle and constant. It rises through volcanic vents, spreads across ocean ridges, and dissipates through the drifting dance of tectonic plates. But Venus lacks this rhythm. Its crust is sealed, its plates immobile. The planet's inner heat has nowhere to go. For billions of years, the planet's molten heart has burned quietly beneath the surface, radiating energy upward, held back by a crust too thick and too strong to break. That heat does not vanish. It collects. It builds tension. And when that tension reaches a threshold, the balance collapses. Scientists believe this process may explain the planet's strange cycle of destruction and rebirth, the alternation between long ages of stillness and sudden catastrophic renewal. The planet's inability to vent its heat gradually forces it into extremes. It waits for geological ages in silence, then releases its stored energy all at once. To understand why, we must return to the physics of the interior. The heat within Venus comes from two primary sources: the leftover energy of its formation and the slow decay of radioactive elements such as uranium, thorium and potassium in its mantle. Every planet has these sources, but on Venus the output is not balanced by efficient cooling. The mantle convects, hot material rises, cool material sinks, but with no tectonic openings above, the heat becomes trapped in vast subsurface eddies. Imagine an ocean of magma swirling endlessly, pushing against a lid of stone. The pressure increases over millions of years, deforming the crust from below. Eventually, the crust can no longer contain it. Fractures spread, magma rises, and the planet begins to vent in catastrophic fashion. This scenario explains why Venus's surface appears both young and uniform. The eruption of heat and lava would have resurfaced the entire planet within a geologic instant, perhaps less than 100,000 years. Then, as the crust cooled and sealed again, the system reset quiet on the outside, restless within. Some scientists liken Venus's behavior to that of a pressure cooker without a valve. As long as the lid holds, the system remains stable. But once the pressure exceeds the strength of the lid, the release is violent and absolute. Evidence for this is written in the planet's geology. Venus lacks deep trenches or spreading ridges, the outlets Earth uses to release heat. Instead, it shows vast plains of basalt and massive shield volcanoes consistent with large-scale prolonged eruptions. Thermal models of the planet's mantle suggest that without tectonic recycling, internal heat could rise to critical levels every few 100 million years. This is the foundation of the catastrophic resurfacing model, one of the two great competing ideas about how Venus renews itself. According to this model, the planet's interior heat builds until the entire crust weakens. When the moment comes, magma floods upward across thousands of kilometers, melting and burying everything in its path. Within a short time, perhaps a few tens of thousands of years, the surface is completely reborn. Then, silence. The eruptions cease, the lava cools, and a new crust forms. For the next several 100 million years, the planet sleeps again, the process beginning anew. This theory explains the random distribution of craters, because the last great resurfacing erased all previous ones. It also accounts for the planet's uniform topography, the product of global rather than local renewal. But it also raises questions. If Venus truly renews itself through cataclysm, what signals mark the build-up to the next one? Can we detect that slow hidden pressure before it erupts again? The alternative hypothesis, the gradual resurfacing model, offers a gentler interpretation. It suggests that volcanic activity never entirely ceases but continues intermittently across the planet, resurfacing areas bit by bit over time. In that version, Venus is not a world of explosions but of endurance, a planet whose heartbeat is steady rather than violent. Both theories begin from the same truth: the planet's heat is trapped. It cannot escape naturally. It must eventually find release. The question is how? Does Venus erupt in catastrophic fury, or does it bleed its energy in quiet persistence? Each model paints a different personality for the planet, one violent, one patient. Yet both share a kind of melancholy inevitability, for in the end neither can save the world from itself. Whether slowly or suddenly, Venus will always return to the same point: heat rising, crust bending pressure, mounting until the surface breaks and begins again. If there is one theory that captures the drama of Venus's history, it is the catastrophic resurfacing hypothesis, the idea that the planet did not slowly evolve but violently remade itself in one global act of destruction. According to this model, the story of Venus is punctuated by long periods of stillness followed by planetary convulsions. For hundreds of millions of years, the crust remains sealed and motionless, while heat builds in the mantle below. Then, without warning, the tension breaks. The crust fractures. Magma rises in waves, flooding plains, swallowing mountains, and reshaping everything in its path. What emerges is a new world, smooth, young, and deceptively calm. The evidence lies not in what we see, but in what we don't. The scarcity of impact craters the even age of the terrain, and the absence of old geological structures all suggest a single global event that erased nearly all traces of the past. In the radar mosaics returned by Magellan, Venus's surface looks uniform, as though someone had melted the entire planet and allowed it to solidify again. There are no continental boundaries, no ancient mountain routes, no surviving relics of older epochs. Everything visible today appears younger than 1 billion years, a blink in geological time. For Earth, the idea of such total renewal is unthinkable. Even our most powerful eruptions, the Deccan traps, the Siberian traps, reshaped only parts of continents. But Venus, lacking oceans and tectonics, could have been consumed by its own internal energy, every volcano joining in a chain reaction of molten release. Computer models suggest how it might have unfolded. As heat accumulates within the mantle, the lower crust begins to soften. Over millions of years, buoyant magma pushes upward, thinning the crust and cracking it from below. The pressure rises exponentially until the crust reaches its breaking point. Then, almost instantaneously, in geologic terms, the entire shell gives way. A deluge of molten rock erupts from fissures that span continents. Lava pours across plains, submerging old surfaces beneath kilometers of basalt. In a matter of tens of thousands of years, the crust is destroyed and replaced. The atmosphere thickens with volcanic gases, carbon dioxide, sulfur dioxide, and water vapor. Temperatures climb higher, still transforming the planet into the furnace we see today. The violence of such an event would have been unimaginable. Sky and ground would become one continuous storm of heat and ash. Lightning would ignite through the sulfur clouds. The air already dense would glow with reflected fire. From orbit, the planet might have appeared like a star, a molten sphere radiating infrared light into space. And then, as abruptly as it began, the fury would subside. The lava would cool, the fractures would seal, the crust would thicken into a new unbroken shell. The planet would fall silent again, its heat trapped once more beneath the hardened skin it had created. This cycle could repeat indefinitely, long ages of dormancy, followed by brief catastrophic renewal. Each resurfacing wipes away the record of the one before, leaving scientists with only the latest layer to study. That is why the surface of Venus seems timeless. We see only its most recent self, unaware of how many worlds may have come and gone beneath. The catastrophic model also helps explain the planet's strange thermal balance. After such an eruption, the thickening atmosphere would trap enormous amounts of heat. The greenhouse effect would intensify beyond recovery, ensuring that the surface never cooled enough for liquid water to return. The crust, once solidified, would become an insulating lid, preserving the mantle's warmth and setting the stage for the next convulsion. Some researchers describe Venus as a planet caught in a cycle of self-devouring. Each eruption feeds its own imprisonment. The gases released during the resurfacing events make the atmosphere denser, which in turn traps more heat, which then causes the next eruption. The planet is locked in feedback between fire and suffocation. Not all scientists accept this model completely. Its scale is extreme, its timing uncertain, and its mechanism still debated. Yet the patterns of the surface, the random distribution of craters, the smooth expanses of basalt, the lack of tectonic scars fit its predictions better than any other theory we have. It portrays Venus not as a quietly dying planet, but as a survivor of apocalypse, a world that has destroyed itself and started over again and again, until what we see today is only its most recent rebirth. And in that story lies something both terrifying and awe-inspiring. A reminder that planets are not static. They breathe, they suffer, they transform. Their lives are not measured only in the slow erosion of time, but in the sudden rewriting of existence. Venus, Earth's twin, may have chosen this violent path long ago, a path of endurance through renewal of memory through destruction. The question that remains is whether this cycle has truly ended, or whether the next great eruption is already gathering strength beneath its quiet surface. For if the catastrophic model is correct, then somewhere deep within the planet's mantle, heat is rising again. And one day, whether in 1,000 years or 100 million, Venus will remember how to burn. If the catastrophic model imagines Venus reborn in a single fiery instant, its quiet arrival tells a different story, one of endurance rather than apocalypse of a planet that changes not in explosions but in whispers. This is the gradual resurfacing hypothesis, the idea that Venus renews itself piece by piece through countless small eruptions scattered across eons. In this model, the planet never truly sleeps. It exhales through slow, steady breaths, each volcanic outflow adding a thin layer of lava to the surface, each eruption erasing a small patch of history. Over hundreds of millions of years, these local renewals accumulate until nearly the entire crust has been replaced. Unlike the catastrophic scenario, there is no single moment of destruction here, no planetary-scale event that melts everything at once. Instead, Venus evolves as a patchwork resurfacing in fragments, one volcanic field at a time. The radar maps from Magellan leave room for this interpretation. Although the planet's surface looks uniformly young, small differences in radar brightness and texture hint at multiple ages. Some plains appear smoother and darker, others slightly rougher, perhaps older, their lava eroded or chemically altered by the dense atmosphere. These subtle contrasts could mark regions that cooled at different times, suggesting that resurfacing occurred gradually, not globally. If this is true, then Venus has never been entirely dead nor entirely reborn. It has always existed in motion, a restless equilibrium between fire and stillness. To visualize it, imagine the planet's surface as a vast mosaic of volcanic provinces. Here a field of lava plains a few million years old. There a corona ringed with fractures where magma once rose and froze. Elsewhere a long rift where molten rock once flowed like a river, solidifying into basalt before another eruption began somewhere else. Over time, these isolated events overlap, covering old craters and reshaping the land in quiet persistence. Each eruption is a moment in a slow, continuous symphony of renewal. This model fits with some of the thermal data from orbiting missions. The Venera Express spacecraft detected variations in surface brightness and infrared emission, faint signs that some regions might still retain warmth, possibly from recent volcanic activity. If eruptions were still occurring, even on small scales, they would be enough to account for the youthful appearance of the surface without invoking global cataclysm. In this view, the 37 coronae identified as potentially active by researchers are not ancient relics but living features, vents, through which the planet occasionally releases its heat. Each one may have awakened many times in the past, adding layer upon layer to the surrounding plains. The gradual resurfacing model paints Venus as an artist of patience. It reshapes itself not with violence, but with constancy, its transformations spread across eons. The process is less spectacular, but perhaps more realistic. The slow outpouring of basaltic lava would allow gases to escape, intermittently sustaining the planet's thick atmosphere without requiring a single world-ending event. Yet this vision carries its own mysteries. If Venus renews itself so slowly, why do the craters remain so evenly distributed? Why does the planet's surface still appear so uniform in age without the patchy diversity we see on other worlds? Some scientists propose a hybrid scenario that Venus undergoes long periods of gradual volcanism, interrupted by occasional pulses of catastrophic activity. The two processes might coexist, slow renewal as a baseline punctuated by sudden planetary upheaval when the heat grows too intense to contain. Others suggest that the surface's uniformity may be an illusion, the product of limited data. The resolution of Magellan's radar, while revolutionary for its time, cannot yet reveal the subtle layering of flows that would confirm gradual resurfacing. New missions like NASA's Veritas and Da Vinci are expected to test these competing ideas by mapping the surface at far higher precision. Still, the gradual hypothesis has a quiet elegance. It describes a planet that survives through balance, not extremes, a world that remembers how to burn but only in slow motion. It does not erupt all at once, it breathes in millennia. Perhaps that is why the face of Venus seems serene despite its hellish heat. The planet's surface, renewed grain by grain, hides its violence behind a calm facade. Each lava flow cools into stillness, each fracture seals, each breath of gas vanishes into the thick golden sky. In this version of history, Venus is not a phoenix rising from its own ashes, but a slow, eternal fire, a world whose transformation never truly stops. The truth may lie somewhere between the two models, between cataclysm and continuity. A planet that sometimes explodes, sometimes exhales, but always endures. And perhaps even now, beneath its clouds, that slow exhalation continues. A vent opens, a flow begins. The surface changes once more, not in fury, but in patience. Venus. The silent twin still remembers how to move. It just moves at the speed of eternity. If Venus truly died long ago, its surface should bear the stillness of eternity, no heat, no change, no whisper of motion. Yet the data tell a different story. Beneath its choking sky, there are hints that something still moves, something still breathes. This idea that Venus may not be geologically dead forms the heart of the living planet hypothesis. It suggests that deep beneath its crust, the fires of the planet are still alive, shaping the surface in ways subtle yet undeniable. The first clues came from Venera Express, the European spacecraft that orbited Venus from 2006 to 2014. Using instruments sensitive to infrared light, scientists peered through the dense atmosphere, searching for differences in temperature and brightness. What they found startled them: patches of terrain that glowed just a little warmer than their surroundings, especially around large volcanic provinces like Matmons, Ozamons and Themis Regio. These thermal anomalies could not easily be explained by sunlight or atmospheric circulation. The simplest interpretation was the most daring, that some of these regions had been recently resurfaced by lava, still radiating the faint warmth of their birth. If so, then Venus's most recent eruptions might not have occurred hundreds of millions of years ago, but perhaps only a few million, or even a few 100,000. In the scale of planetary history that is not ancient, it is now. Infrared data alone could not prove this, but the numbers were compelling. Some flows appeared to have ages between 250,000 and 2.5 million years, astonishingly young for a planet long thought extinct. Even more intriguing was the discovery that many of these flows coincided with regions of known mantle, upwelling the same zones where coronae and volcanic domes are concentrated. Venus, it seemed, was still warm in all the right places. The signs did not end there. Scientists revisited Magellan's radar data from the early 1990s, comparing images taken at different times. In a few regions, subtle changes appeared, patches that had brightened or darkened over the course of just 2 years. One site near the volcano Mat Mons showed a vent that seemed to have changed shape, expanding slightly and altering its reflective signature. The possibility emerged a volcanic eruption had occurred between 1990 and 1992, during the very mission that mapped the planet. If that finding holds, it would make Venus the second actively volcanic world in the solar system after Earth, and the only one shrouded in permanent cloud. Of course, scientists tread carefully. Radar data are delicate. Artifacts can mimic change. But the coincidence between radar variation, infrared hotspots, and known volcanic features is difficult to ignore. The evidence, though circumstantial, begins to converge toward one conclusion: Venus still burns. If the planet is indeed active, its behavior challenges everything we thought we knew about its evolution. A living Venus means a mantle still convecting, still generating pressure. It means the crust is not entirely sealed, but occasionally cracks, letting magma leak upward in slow pulses. It means the planet is not frozen in geological time, but part of a dynamic continuum, a system in balance between silence and eruption. The presence of modern volcanism would also help explain the composition of Venus's atmosphere. The high levels of sulfur dioxide, for example, fluctuate over decades, suggesting an ongoing source replenishing it from below. On Earth, sulfur dioxide is a direct signature of volcanic activity. Its persistence on Venus, despite the planet's dense winds and chemical reactions, implies that new emissions continue to rise. Some researchers even speculate that Venus's atmospheric chemistry operates like a barometer of its internal life. Each shift in sulfur, each subtle change in brightness or temperature might be the planet's way of signaling from beneath its veil. To think that such signals may have gone unnoticed for centuries hidden behind the clouds that make Venus both blindingly bright and eternally obscure is humbling. We are only now learning to read its language: a flicker in heat, a shimmer in radar, a rise in gas. The living planet hypothesis does not claim certainty. It offers a possibility that Venus, despite its infernal conditions, is not a corpse but a cocoon. That somewhere under those thousands of kilometers of rock and gas, a molten heart still beats. In this view, the planet's stillness is an illusion. Its silence is a mask. Every ripple of heat, every faint chemical anomaly becomes part of a larger rhythm, the slow pulse of a world that endures through fire and pressure. Perhaps that is the greatest irony in the place we call dead life. Geological life persists in its most primal form, a reminder that even hell can move, that even silence can burn. Sometimes the greatest discoveries sleep in old data, waiting for the right eyes, the right algorithms, or the right questions to wake them. For Venus, that awakening came 3 decades after the Magellan spacecraft fell silent. Between 1990 and 1994, Magellan orbited Venus and painted it with radar pulse after pulse sweeping across the planet's shrouded face. At the time, it gave humanity the first near-complete map of the Venusian surface, a landscape of volcanoes, lava plains, and fractures that seemed frozen in time. But to most scientists then, Venus appeared geologically dormant, a still world, a monument to what once was. It took 30 years and a new generation of analysis to change that story. In 2023, researchers revisited Magellan's old radar images with modern processing tools, sharper algorithms, cleaner corrections for atmospheric distortion, and the patience to compare the same regions pixel by pixel. What they found in one unremarkable area near Mat Mons was a transformation no one had noticed before. 2 images taken roughly 8 months apart showed a vent, a volcanic opening that had changed shape. In the earlier image, it was circular, smooth with clear walls. In the later one, it had expanded, its interior darkened, and a new bright patch extended downslope as though something had flowed outward. The The simplest explanation was the boldest one: a volcanic eruption had occurred between February and October of 1991. If true, it would be the first direct evidence of an active volcano on Venus, not an ancient remnant, not an inference from temperature, but a real event caught in the act, written into the planet's radar echoes. The region in question lies in Atla Regio, one of the planet's most volcanically complex areas. The vent itself belongs to Mart Mons, a colossal shield volcano that rises nearly 9 kilometers above the plains, roughly equivalent to the height of Earth's Mount Everest, plus Mauna Loa stacked together. For decades, Mart Mons had been suspected as a possible site of activity based on its structure and proximity to other volcanic features. But suspicion is not proof. Now the images offered something close to confirmation. When the Magellan radar beam hit the altered vent, the reflected signal brightened and darkened in ways consistent with newly formed rock, smoother, denser, and still relatively unweathered by the harsh Venusian environment. For the first time, the planet seemed to have moved before our eyes. The finding reignited an old question. Had Magellan seen other such changes that no one noticed? Researchers began scanning the vast archives again. Thousands of overlapping swaths of data, each a ghostly radar reflection of the same fiery world. Patterns began to emerge: minor changes in brightness here, a slight shift in topography there. None as clear as Mart Mons, but enough to suggest that the 1991 eruption might not have been unique. If multiple eruptions occurred within a few years, Venus could be more volcanically active than we ever imagined, perhaps, with dozens of ongoing or recent vents. Skepticism, however, remains an essential part of science. Some argue that the apparent changes could result from variations in radar viewing angle or processing errors, but even critics admit that the evidence is persuasive, especially when paired with infrared observations from Venera Express and chemical fluctuations in the atmosphere recorded decades later. If those separate lines of evidence all point to the same regions, Mart Mons, Ossa Mons, Themis Regio, then coincidence becomes less likely. Something in those zones is alive. A living Venus is not just a matter of academic fascination. It changes how we think about planetary evolution itself. It means that the forces shaping Earth mantle convection, volcanic outgassing, crustal renewal still operate on our twin world under far harsher conditions. It also means that the boundary between active and dead planets is blurrier than we thought. And perhaps most hauntingly, it means that the surface we see today is not the final layer. There could be lava flows hardening even now beneath the suffocating clouds. The crust could be shifting in microscopic ways, preparing for the next breach. The planet's own history might be unfolding at this very moment, invisible to us, hidden behind a veil of light and acid. If Magellan indeed captured a volcanic eruption in 1991, then our entire perception of Venus changes. It is no longer a relic, it is a contemporary world unfolding in parallel with our own. Somewhere even now, new land may be forming. A vent may be widening. Gas may be rising from molten stone into that dense golden sky. And as we re-examine the past, we realize that Venus was never truly silent. We were simply not listening closely enough. The planet's radar echoes still hum with data, billions of reflections, each holding a fragment of motion. Within those whispers, the story of a living world waits to be told. It is there in those subtle shifts of light and form that we find the most humbling truth. Sometimes the universe does not reveal its miracles in the new, but in what we already possess, waiting quietly for us to notice. If Venus still moves beneath its crust, then the evidence should not only lie in stone, it should be written in air. Even through the planet's thick atmosphere, we can listen for breath. The gases above the clouds, the trace elements drifting in sunlight, all carry secrets from the world below. And in recent years, those whispers have grown louder. For decades, planetary scientists have monitored Venus's atmosphere using both ground-based telescopes and orbiting probes. It is a cauldron of carbon dioxide, nitrogen, and sulfur dioxide, its layers stacked in chemistry and chaos. But when researchers compared data across decades, they noticed something strange. The amount of sulfur dioxide, one of the key volcanic gases, changes over time. That should not happen on a dead planet. Sulfur dioxide, SO2, is unstable in Venus's upper atmosphere. Ultraviolet radiation from the sun breaks it apart within weeks. Without a source to replace it, the gas should have disappeared long ago. Yet missions like Pioneer Venus in 1978 and Venera Express in the 2000s found that its concentration fluctuates, sometimes doubling, sometimes falling sharply. Each rise, each spike may be a sign of volcanic exhalation, bursts of gas released from below carried upward through the dense superheated air. In other words, Venus breathes. On Earth, volcanic eruptions inject sulfur dioxide high into the atmosphere, where it forms reflective aerosols that cool the planet. On Venus, that same process works in reverse. Instead of cooling the thick air traps, the heat feeding the runaway greenhouse effect. But the mechanism is similar. The chemistry of the sky becomes a record of the ground's restlessness. When Venera Express observed Venus in infrared light, it found not only variations in surface heat but also patterns in atmospheric composition above certain volcanic provinces. The correlation was striking. Regions with higher infrared brightness, suspected of recent lava flows, also showed elevated sulfur dioxide and unusual cloud opacity. In 2012, scientists analyzing these results proposed that Venus might still experience eruptions every few decades, releasing pulses of gas large enough to change the chemistry of its atmosphere. That would mean the planet's last breath may have happened not in the ancient past, but within living memory. To test this idea, researchers have begun comparing atmospheric data with radar and thermal maps. When patterns overlap, when heat and gas align, a story emerges. Each fluctuation becomes a syllable in the planet's hidden language pressure: fracture, eruption, release, renewal. Yet Venus is no easy world to read. Its atmosphere churns with super-rotation hurricane winds that circle the planet every 4 days, faster than the planet itself turns. These winds smear out local signatures, blending the distinct breath of volcanoes into a global haze. Distinguishing a single eruption's plume from the background chaos is like hearing a whisper in a hurricane. Still, the chemistry persists. Even from afar, Earth-based observatories like the Infrared Telescope Facility in Hawaii have detected hints of variable gases, sulfur dioxide, carbon monoxide, and possibly even transient compounds that form when fresh volcanic gases interact with sunlight. Each detection, though debated, keeps the question alive: how much of Venus's atmosphere still comes from its interior? One of the most intriguing connections lies in the balance between sulfur dioxide and water vapor. Both are volcanic products, but water is fragile here. It quickly splits into hydrogen and oxygen under ultraviolet radiation. If new water molecules appear even briefly, they must come from below. That would mean active outgassing, an unmistakable fingerprint of internal motion. The prospect electrifies scientists. If Venus still emits volcanic gases today, then its deep interior remains molten convective dynamic. It means the same heat that reshaped its surface still breathes upward through its clouds. It means the planet is not a tomb, but a furnace. Every pulse of sulfur, every shimmer of thermal light becomes a heartbeat. And yet there is a quiet beauty in this violence. The gases that make Venus uninhabitable are also the reason we can study it at all. Without them, the planet would radiate too faintly to detect from Earth. It is as though the planet's own fury illuminates its face, allowing us to see it, a self-lit mirror of geological passion. Venus's atmosphere is in essence its confession. It tells of past eruptions, of flows now buried under basalt plains of fractures that once glowed. It reminds us that even behind a veil of acid and carbon, a planet's heart can still speak. And perhaps this lesson extends beyond Venus. When we search distant worlds orbiting other stars, we too look for atmospheric anomalies, chemical imbalances, traces of gases that do not belong. On Earth, life creates such signals. On Venus, it is geology. But in both cases, the principle is the same: imbalance means activity. Change means motion. Motion means life in one form or another. So when we observe Venus and see the dance of its sulfur clouds, we are not just watching weather. We are witnessing breath. The breath of a planet that refuses to die. A furnace that still exhales into the void. A reminder that beneath even the most silent skies there can still be a pulse. It has been more than 30 years since Magellan fell into the clouds of Venus and was swallowed by fire. The echoes of its radar still drift in our data archives, faint reflections from a world we can no longer see, a world that might still be moving beneath its shroud. For a generation, those images were all we had. Grainy mosaics, streaks of brightness and shadow, a puzzle of rock beneath sulfur skies. They were enough to reveal a planet of volcanoes, mountains, and endless plains of basalt. But they were not enough to tell us if that world still lives. Every question that matters remains suspended there unanswered, like a signal lost in static. Is Venus's surface still reshaping itself even now? Do Do rivers of lava still flow in silence concealed by the mist? Or is all that heat we measure just the ghost of an ancient catastrophe? For decades our eyes have been blind to change. No new radar, no fresh measurements, no whisper of heat confirmed. The maps of Magellan, now older than an entire generation of scientists, have become both relic and prophecy, a frozen image of a planet that refuses to stay still. And so the time has come to look again. Humanity is preparing its second vision of Venus, a new fleet of machines that will orbit closer, see sharper, and listen deeper than ever before. They will not only map the surface but study its pulse. They will descend through the atmosphere, tasting its air, recording the chemistry of its breath. For the first time in half a century, we will not just infer, we will witness. The call for new eyes is not merely technological, it is philosophical. We have learned that silence is not proof of stillness, that absence of evidence is not evidence of death. If Venus has taught us anything, it is that worlds can whisper for eons before we learn how to listen. What if the signals have been there all along, hidden in spectra, buried in old radar frames, woven into clouds of sulfur and light? What if Venus has been alive this whole time, waiting for us to notice the faint motion beneath the static? This is what the next decade will answer. NASA and the European Space Agency are sending 3 emissaries, Da Vinci Veritas and Envision, each designed not just to observe but to reveal. Together they will act as a chorus of instruments, each tuned to a different frequency of truth. Da Vinci will fall, Veritas will orbit, Envision will listen. Each will look for signs of renewal, chemical fingerprints, surface shifts, hints of heat, the smallest tremors of a planet that might still be alive. Because to see Venus again is not just to study another world, it is to confront our reflection. Earth's twin, same size, same density, same beginning, diverged not because of chance but because of balance. A little more sunlight, a little thicker atmosphere, and everything changed. Where one world cooled, the other boiled. Where one nurtured life, the other became its mirror of extinction. And yet that mirror may not be as lifeless as it appears. Every anomaly we've found, every sulfur fluctuation, every faint patch of warmth, every darkening vent hints that Venus is not frozen in its fate. Something stirs beneath its crust. Something perhaps is still remembering how to move. The call for new eyes is a call to humility. We must learn to see again, not with expectation but with patience. To listen to the data not as static but as rhythm. To understand that a planet can speak in intervals of millions of years, and we must learn to match its pace. When Da Vinci enters its clouds, it will descend through sulfuric rain and crushing pressure, carrying sensors that can detect gases to the precision of a single molecule. When Veritas unfurls its radar in orbit, it will watch for surface changes so small they could fit inside a footprint. When Envision begins its long survey, it will feel for gravitational tremors that betray movement in the mantle. Together they will give us something Magellan never could, not just a snapshot but a heartbeat. And if we find that heartbeat, faint as it may be, we will know that Venus never truly died. We will know that beneath that sea of heat and acid, the planet is still remaking itself, still trading energy with the cosmos, still alive in the most primal geological sense. To some, that discovery will mean vindication, to others, warning. For if Venus, our twin, can still burn after everything it has endured, then what of us? Perhaps the real reason to return is not to solve a mystery of geology, but to face a mirror of destiny, to ask what does it take for a world to survive itself. The call for new eyes then is also a call for new understanding, to see motion not as chaos, but as persistence, to see destruction not as an end, but as transformation. Because in the end, Venus is not just a planet. It is a question, one we must learn to answer slowly, reverently, with eyes that no longer assume silence means death. We mapped its skin once, now we must read its pulse. They are already being built, the second generation of messengers forged to see through fire and cloud. Where Magellan saw only in radar shadows, these new explorers will look in layers, heat, chemistry, movement, time. Together they will reopen the story of Venus, the twin world that has hidden its heartbeat for too long. Their names carry the weight of vision and purpose: Da Vinci, Veritas and Envision. 3 voices of a new age of planetary inquiry, 3 eyes turned toward a shrouded sister. They will not simply look, they will listen, they will measure, they will remember. Da Vinci, the deep atmosphere. Venus, investigation of noble gases. Chemistry and imaging is unlike any mission before it. It will not orbit, it will fall. A small sphere encased in heat-resistant alloy will detach from its carrier spacecraft and descend into the clouds, like a question cast into the depths. At first, it will drift through the pale upper layers where sunlight still glows, and the air is only slightly more crushing than that of the deepest ocean on Earth. But the deeper it sinks, the darker it becomes, pressure rising, the air thickening, the colour shifting into molten amber. Each kilometre down is a century in pressure. Within that descent, the probe will take its final breath of sunlight before vanishing into the golden fog. In that hour-long fall, Da Vinci will measure everything. It will taste the atmosphere for noble gases, argon and krypton, and analyse their isotopes to tell how Venus's air was born, whether it once mingled with oceans, or whether those oceans ever existed at all. It will measure sulfur and carbon compounds, searching for the telltale chemical imbalance of a planet still alive inside. Each molecule it captures will be a fossil of motion proof that the planet still exhales. And in its final minutes, the probe's small camera will pierce through the haze, showing what no human eye has seen in half a century: the true surface of Venus' jagged basalt plains, glowing in orange light, a horizon warped by pressure, a sky like liquid fire. The probe will not survive, no craft can. The heat will rise beyond 460 degrees Celsius, the pressure 90 times that of Earth. Metal will soften, circuits will die. Yet in that brief fall, it will send home a flood of truth, 1 hour of data that could rewrite the history of an entire planet. While Da Vinci dives, Veritas, the Venus Emissivity Radio Science INSAR topography and spectroscopy mission, will take its post above the clouds. If Da Vinci is the breath, Veritas is the gaze. Its radar will be the sharpest ever aimed at Venus, mapping every hill and fracture in exquisite detail. Unlike Magellan's single sweep, Veritas will revisit the same places again and again, comparing each image with the last. Its interferometric radar INSAR will detect even the smallest movements, measuring the rise and fall of the surface to the scale of centimetres. It will see if volcanoes have shifted, if plains have sagged, if cracks have widened, the subtle signs of a crust that still flexes beneath unseen heat. It will also carry an infrared spectrometer to detect thermal radiation and mineral composition. It will distinguish new rock from old fresh lava from cooled basalt by the way each reflects invisible light. With every orbit, Veritas will compare the present to the past. Against Magellan's maps from 1991, it will test whether anything has changed. If Venus truly remains active, then even a few new lava flows a small landslide, or a shifting vent will betray the movement of its heart. The radar will not lie. It will measure time through stone, and with each pass it will refine our understanding of how Venus renews itself in sudden planetary convulsions or in slow volcanic whispers. Veritas's mission is aptly named Truth. Not just truth of image, but truth of process of endurance. Its orbit will turn again and again over the same burning plains, collecting years of data, listening to the slow pulse of geology. From this, scientists will test both great hypotheses, catastrophic resurfacing, or gradual renewal, a planet remade in fury, or one that evolves through patience. The radar will decide. Then there is Envision Europe's answer to the question that refuses to die. If Veritas observes the surface, Envision will probe what lies beneath. Using a suite of radar and gravity instruments, it will sense the inner structure of Venus, the unseen architecture of a world that may still convect with molten energy. By mapping tiny fluctuations in the planet's gravitational field, Envision will detect movements in the mantle, hidden plumes of magma, and the faint flexing of a crust under pressure. These are the deep signatures of life in stone, the motions that never reach the surface but define it. Envision will orbit lower than any mission before it's skimming the atmosphere until it can feel the drag of the dense air below. Its sensors will measure the exchange of gases between surface and skytrack, changes in sulfur dioxide and water vapor, and monitor the turbulence of the upper clouds. If Venus still exhales heat or gas, Envision will hear it. It will sense the breath that Da Vinci will taste and Veritas will see. Together, these three missions form a perfect triangle: air, surface, and interior, each one completing the others, each one translating a different language of motion. When their data combine, the picture will be whole. For the first time, we will not only map Venus's geography but witness its physiology, a system alive with heat and feedback where stone, gas, and gravity form a single rhythm, the rhythm of a world remembering how to move. If they succeed, they will not just answer the scientific question whether Venus is active today. They will answer something larger, They will show us how fragile a planet's balance can be, how easily air can turn to fire, how thin the line between Earth and Inferno truly is. Imagine it in the next decade, images arriving from orbit, a lava field that changed shape, a vent that widened a patch of infrared heat where once there was none. Imagine a descent capsule sending in its final moments the chemical breath of a world that has not stopped exhaling. For the first time, we might see a planet's evolution unfold in real time, not the slow patience of geological centuries, but the living, breathing moment of transformation. But even if the missions find nothing, if no flow moves, if no gas rises, the act of returning still matters. To look again is to refuse complacency, to accept that knowledge is always incomplete. Venus reminds us that silence is not proof of death, that what we call stillness may only be motion too slow for our eyes. Perhaps that is the truest reason for these journeys, not only to uncover facts, but to rediscover wonder, to see through cloud and fire and find that even in the harshest worlds there remains something worth listening to. Da Vinci will fall, Veritas will orbit, Envision will listen. 3 instruments, 3 questions, 1 heartbeat waiting to be heard. When they speak together, Venus will finally have its voice restored, a symphony of data and silence, light and radar chemistry and fire. And when we listen, we may realize that the story of Venus was never just about another planet. It was about us, about learning to see motion again, to find life not in water or biology, but in energy, endurance and change. What began as myth will end as revelation. The morning star will rise once more, not as a goddess or a warning, but as a truth. A world that burned to live. They were born together, 2 worlds forged from the same cloud of dust and flame, 2 sisters circling the same star. In their youth, they might have looked alike, both blue, both wrapped in soft clouds, both holding oceans that shimmered beneath a young sun. But somewhere long before we learned to look back at them, one began to drift toward ruin. Venus and Earth twins in form, opposites in fate. One cooled just enough for water to remain, for life to rise and sculpt its surface. The other, only slightly closer to the sun, crossed an invisible line. Its oceans boiled its skies, thickened its air, turned to poison. The balance broke, and from that day on the sisters lived apart, one breathing with biology, the other burning with memory. To study Venus is to study loss, not the absence of life, but the transformation of potential into permanence. Its mountains and plains are the monuments of a planet that once might have been like ours, a planet that still remembers how to move but no longer knows how to cool. Perhaps the greatest paradox is this: the very processes that sustain life on Earth are the ones that destroyed it on Venus. Heat that drives tectonics here built a trap there. Volcanism that refreshes our air has suffocated theirs. Greenhouse gases that nurture our climate run wild on that twin-turning sunlight into unending fever. It is a mirror of warning. Every time we measure the carbon in Venus's skies, the sulfur, the fire, the weight of pressure, we are also measuring the distance between survival and collapse. A few degrees, a few molecules, a few billion years of imbalance that is all it takes to turn a paradise into a furnace. And yet there is something profoundly human in this reflection. Because Venus is not dead. It moves. It breathes in geologic time, in slow pulses of heat and change. Beneath its clouds, it is still alive in the way only worlds can be, through the exchange of energy, through motion, through transformation. It has endured every catastrophe it created, and still it turns, still it glows, still it remembers. When we send our new eyes, Da Vinci Veritas, in vision, we are not just searching for data, we are searching for meaning, for proof that even in destruction there can be persistence, that a world can lose everything we recognize as life, yet still hold the memory of creation in its molten core. Perhaps that is what Venus teaches best: to live is to change, to burn is to endure. Planets, like people, are not defined by stillness, but by how they continue to move after they have been broken. Scientists often say Venus is what happens when a planet goes wrong. But maybe that is too simple. Maybe Venus is what happens when a world refuses to stop evolving, even after its oceans have vanished, even after its sky has become a storm of acid and flame. It remakes itself in every epoch, erases its scars and begins again. That is not failure, that is resilience. And in that resilience lies its kinship with us. For Earth too lives on the edge, balanced between fire below and frost above, between chaos and order, between breath and silence. To look at Venus is to glimpse what waits if we lose that balance, not a prophecy of punishment, but a reminder of responsibility. If we can learn to read Venus, its heat, its air, its rhythm, we can learn how to preserve our own fragile equilibrium. Every signal it sends is a lesson of feedback of limits of transformation. Its surface may be too hostile for us to stand upon, but its story is carved into the same cosmic laws that hold us. And when we listen, truly listen, we hear not a warning alone, but an echo. The same physical heartbeats that move our Earth are still pulsing there, slower, heavier, buried in rock and acid, but alive. Venus is not our opposite. It is our reflection in another time. It shows what might happen and what still might be saved. In a way, Venus is the most human of planets. It is flawed, restless, full of contradictions. It has burned itself, and yet it endures. It hides its face, yet cannot help but shine. It is our twin, the one that carries our fears into the heavens and shows them back to us in light. Perhaps when the first images arrive from Da Vinci's Descent, when we see the sharp ridges and amber glow of its plains, we will feel not alienation, but recognition. The same forces that shaped us shaped it. The same chemistry that sustains our world destroyed that one. And yet through it all, both still circle the same sun, bound by gravity and time, twin testaments to what it means to exist in an unstable universe. Venus may never bear life as we know it, but in the language of matter, motion is life. Heat is life. Change is life. The same pulse that drives magma beneath its crust drives the breath in our lungs. We are made of the same restlessness. So when we call Venus the planet that burned to live, we are not speaking in metaphor. We are acknowledging a truth older than biology, that existence itself demands energy, and energy is always on the edge of destruction. Maybe every planet remembers what it means to live, and maybe every life, every civilization must learn what it means to burn. If Venus could speak, perhaps it would not warn us. Perhaps it would only whisper, "I am still here," and that in its quiet way would be enough. They were born together, two worlds forged from the same cloud of dust and flame, two sisters circling the same star. In their youth they might have looked alike, both blue, both wrapped in soft clouds, both holding oceans that shimmered beneath a young sun. But somewhere long before we learned to look back at them, one began to drift toward ruin. Venus and Earth twins in form opposites in fate. One cooled just enough for water to remain, for life to rise and sculpt its surface. The other, only slightly closer to the sun, crossed an invisible line. Its oceans boiled, its skies thickened, its air turned to poison. The balance broke, and from that day on the sisters lived apart, one breathing with biology, the other burning with memory. To study Venus is to study loss, not the absence of life, but the transformation of potential into permanence. Its mountains and plains are the monuments of a planet that once might have been like ours, a planet that still remembers how to move but no longer knows how to cool. Perhaps the greatest paradox is this: the very processes that sustain life on Earth are the ones that destroyed it on Venus. Heat that drives tectonics here built a trap there. Volcanism that refreshes our air has suffocated theirs. Greenhouse gases that nurture our climate run wild on that twin, turning sunlight into unending fever. It is a mirror of warning. Every time we measure the carbon in Venus's skies, the sulfur, the fire, the weight of pressure, we are also measuring the distance between survival and collapse. A few degrees, a few molecules, a few billion years of imbalance that is all it takes to turn a paradise into a furnace. And yet, there is something profoundly human in this reflection. Because Venus is not dead. It moves. It breathes in geologic time in slow pulses of heat and change. Beneath its clouds, it is still alive in the way only worlds can be, through the exchange of energy, through motion, through transformation. It has endured every catastrophe it created, and still it turns, still it glows, still it remembers. When we send our new eyes, Da Vinci, Veritas, Envision, we are not just searching for data, we are searching for meaning, for proof that even in destruction there can be persistence, that a world can lose everything we recognize as life, yet still hold the memory of creation in its molten core. Perhaps that is what Venus teaches best to live, is to change, to burn, is to endure. Planets, like people, are not defined by stillness, but by how they continue to move after they have been broken. Scientists often say Venus is what happens when a planet goes wrong. But maybe that is too simple. Maybe Venus is what happens when a world refuses to stop evolving, even after its oceans have vanished, even after its sky has become a storm of acid and flame. It remakes itself in every epoch, erases its scars and begins again. That is not failure. That is resilience. And in that resilience lies its kinship with us. For Earth too lives on the edge, balanced between fire below and frost above, between chaos and order, between breath and silence. To look at Venus is to glimpse what waits. If we lose that balance, not a prophecy of punishment, but a reminder of responsibility. If we can learn to read Venus, its heat, its air, its rhythm, we can learn how to preserve our own fragile equilibrium. Every signal it sends is a lesson of feedback, of limits of transformation. Its surface may be too hostile for us to stand upon, but its story is carved into the same cosmic laws that hold us. And when we listen, truly listen, we hear not a warning alone, but an echo. The same physical heartbeats that move our Earth are still pulsing there, slower, heavier, buried in rock and acid, but alive. Venus is not our opposite. It is our reflection in another time. It shows what might happen and what still might be saved. In a way, Venus is the most human of planets. It is flawed, restless, full of contradictions. It has burned itself and yet it endures. It hides its face yet cannot help but shine. It is our twin, the one that carries our fears into the heavens and shows them back to us in light. Perhaps when the first images arrive from Da Vinci's Descent, when we see the sharp ridges and amber glow of its plains, we will feel not alienation, but recognition. The same forces that shaped us shaped it. The same chemistry that sustains our world destroyed that one. And yet through it all, both still circle the same sun, bound by gravity and time, twin testaments to what it means to exist in an unstable universe. Venus may never bear life as we know it, but in the language of matter, motion is life, heat is life, change is life. The same pulse that drives magma beneath its crust drives the breath in our lungs. We are made of the same restlessness. So when we call Venus the planet that burned to live, we are not speaking in metaphor. We are acknowledging a truth older than biology, that existence itself demands energy, and energy is always on the edge of destruction. Maybe every planet remembers what it means to live, and maybe every life, every civilization must learn what it means to burn. If Venus could speak, perhaps it would not warn us. Perhaps it would only whisper, "I am still here," and that in its quiet way would be enough. Beneath those amber clouds, Venus still turns slowly around the sun, a planet that no longer sleeps, yet no longer dreams. From afar it shines like the morning star, but its light is only a reflection of the inferno within a world where rock flows like water and heat becomes memory. We call it a dead planet, but perhaps Venus never truly died. It simply changed the way it exists from visible life to the life of motion, of energy, of endurance. Every current of air, every surge of heat is a slow heartbeat, a quiet whisper of a world still remaking itself in solitude. And when we turn our radar toward it, when we listen to the echoes rising from its restless surface, we are not just hearing the story of Venus, we're hearing the echo of Earth, of what might come to pass if our fragile balance ever breaks. Venus is no longer just a warning. It is a memory of fireproof that even in destruction there can be persistence. It still turns, it still shines, and in that silence it still breathes.